All right, so we're going to be talking about function notation and functions in general. So to define what a function is, first we have to talk about what a relation is. So relation is like a big family of functions. Sorry, a big family of things. Okay, so this is relations. And then functions, which is what our whole course essentially is about, as a subsection of relations. So this is functions. I'm not going to be able to fit the whole word in. Just put a capital F for functions. Okay, so relations is like a really big category, and functions is a subcategory. So relation is any set of data. Example, a set of points, an equation, a graph, or a table of values. Okay. A function is a relation where each x coordinate has only one y coordinate. Okay? So for every x value, there can only be a single y value. So let's see what that means as we look at identifying whether or not some of these are functions here. So this first one here, is it a function? So we can see our x and our y, right? So just to refresh our memory here, right? We always write our x's first. That's x, and this is our y. So we have an x value of 1, a y value of 2, an x value of 3, a y value of 4, an x value of 5, a y value of 4, an x value of 6, and a y value of 1. So once again, it's a function if each x coordinate has only one y coordinate. So there's no x coordinate here that has has more than one y value. They all have a singular y value. Let's contrast that with this second set over here. So here we have 4 points again. We have 5, 4, 8, 7, 2, 3, and 5, 1. So here, if we look, the x value of 5, if x is 5, what's y? Well, if x is 5, then y is 4, but it's also 1. So this x value of 5 has 2 y values. Okay, so x equals 5 means that there's y equals 4 and 1. Okay, so this is not a function. So is this a function? This one here is a no. It's not a function because an x value has 2 y values. X value of 5 has 2 y values, 4 and 1. This one is a function. There is no such case. All right. So we can tell that from this is which would be called a set of ordered pairs or just a list of points. If we had a table of values, it's almost the same thing, right? We can tell it from that as well. But usually we look at like graphs. So let's draw some quick graphs and try to identify whether or not they're functions. So let's start with something we're all very familiar with. And we aren't going to be very specific on our exact points here. But let's draw a parabola. All right. So we got a beautiful parabola going. And we want to know whether or not this is a function. So once again, let's go to our definition. Scroll up here. So for each x coordinate has one y coordinate. So let's just think about some of these x coordinates for a second. So let's think of the x is 3. So x is 3 is right here. It's a little blurry on this graphic here, but this is x is 3. So all along here, we end up with a vertical line of where our graph might have an x value of 3, and our graph has an x value of 3, and let me just circle the little spot right up here, and it looks like it has a value of 3 at right around 6. The exact point is not very important in this instance. Okay? So is there a second value? Is there only one value? Well, in this quadratic, this graph, there only appears to be a single y value for the x value of 3, and we can do that with other points too. So we go to -2. We have a single y value along our vertical line here that is of x equals 2, and we could continue to do that, and it would appear that there's always just going to be one y value for all of our x values. Now that doesn't mean that there'll always be one. In this specific case, the domain, as we recall from last week, that is all real numbers. So any x value is going to have exactly one y. Okay, now note, so this, first of all, this is a function. Now, note for a second, the same cannot be said about y's. So if I have a y value of 5, I get an x value over here, and I get an x value over here. Okay, that's fine. Functions don't care if there's more than one x for a single y. They care if it's the other way around. So for each x, there can only be one y. For each independent variable, there can only be one dependent variable. Okay, let's draw another one. Let's draw a circle. So don't worry about how amazingly accurate your circle is. Mine won't be great. Good enough. Okay, so let's think about this one. So let's take an example. Let's just go with x is 0. If x is 0, so along this line, which is along the y-axis, it looks like we can have more than one y value. We get a y value up here and up here. So this is not a function. No. Okay. So we can tell, that's how we're going to identify whether or not graphs are functions, is by these vertical lines. And that's what brings us to our next thing, which is the vertical line test. Okay. So the vertical line test is this. Okay. If every vertical line crosses the graph no more than once, so that means 1 or 0 times, it's a function. It is a function. Okay, so vertical line test here. If we drew a bunch of vertical lines on our circle, we usually get 2 points. There will be some spots where we'll only get one crossing, right? If we go right at the edge here, we'll get one crossing. If we go over here, we'll get 0 crossings. 0 is fine, 1 is fine, but once we have any line that crosses it more than twice, that means that for that x value, there's 2 y values, which means it's not a function. So in some ways, the vertical line test is less a test to see if something is a function. It's more of a test to see if something's not a function. Okay, so the next thing to talk about is function notation. So we have a special way of writing functions. And it looks like this. It's got a more cursive f. Usually, sometimes we use other letters, but for now we'll stick with f's. So f, and then in brackets past that we have our independent variable, in most instances an x. Okay, so we say this as f of x. That is the way we say this thing here, f of x. Okay, and the nice thing about using this notation, and if we look at our examples down here, we'll come back, we write it out like this, and basically we're just replacing y with this f of x. And the thing that we'll see in our example that's nice is this pairs the independent variable with the dependent result of it. Okay, so this pairs the independent, oh my goodness, I'm screwing myself up here, independent and dependent variables in our notation. So our notation being just like the style in which we're writing out our math. Okay, so let's do these two sections here. This is how we used to do a question. We would say something like this, y equals 2x squared plus 7x minus 9. And then we might have a question like, find y when x is 3. And let's go through that. So we might say, well, then y is going to equal 2 times 3 squared plus 7 times 3 minus 9. Okay, and then y equals, let's see, that's going to be a 9. So that's 2 times 9 is 18. 3 times 7 is plus 21 minus 9. And we'd say y equals 30. If we do add all those things together. I'm skipping a few of the simple algebra steps, but okay, that's it. I mean, it's not hard. It's just plugging in a number, you solve it. Let's see how we do it on the other side. Spoiler, we do the exact same thing. So we'd write f at 3. So we say this a little bit different. Here we say f of x. Here we say, let me write it in quotes again for us, f at 3. Okay, so f at 3, the function at 3 is like the long form. The function at 3 is just going to be 2. And we just replace all the x's with 3's, just like we did before. Plus 7 times 3. I always replace things in brackets. It makes the algebra a lot easier. And we do the same thing. We're going to get 18 plus 21 minus 9. And we'll just keep our f at 3 over here. And the last thing we do is we do our collect like terms and just simplify that right side. We get f at 3 is 30. Okay, and we're done. Okay, now a very common mistake you do not want to make is to say, oh, well, I need to solve for the unknown f and divide both sides by 3. Okay, we don't do that. We just leave it like this. So this isn't two mathematical things. This isn't an f being multiplied by a 3. This is a whole mathematical statement by itself. The function at 3 is equal to 30. And you'll notice that if we just look at the two last lines, here and here, then this one contains our independent 3 and our dependent 30 all in one line. And this one, it just says y equals 30. But I'd have to look back in the question to find what x was. Okay? So that's one of the algebraic advantages for us for now. There's some other things that function notations helps with in the future, particularly in more advanced courses. All right, that is all for today, or this lesson. There's more today.